Hello, in this lesson, I wish to go over some more examples. I will take some questions from the homework to show you how to find limit at infinity and how to determine. And before that, I took out this property that we learned in earlier sections, which is about, when x is approaching a. In fact, this theorem also would work for limit at infinity. So that statement can be said as theorem. Okay. And if f is continuous, at b. Okay. And so that's condition, that's the first, that's the first premise, right? So if I can put this as premise number 1 and premise number 2, right? This limit would be limit as x approaching infinity. Okay, if x approaching negative infinity, this will be similar. So g of x is b. Okay, f is continuous at b, right? So b is in the domain. So this also indicates that b is in the domain. And then, and the limit of this composite function when x is approaching infinity, right? F of g of x will be equals to, so we can bring the limit across the continuous function. This theorem is very useful. Okay, and bring it to g of x, right? And bring the limit right here. Okay, we talked about the theorem before, and so this theorem is also very useful. And in fact, we're going to use it in this section. Okay, in this lesson. Take a look at one of the homework questions. It goes like this. It goes like this. Okay, limits as x approaching infinity. Okay, we have a square root of 9x raised to the power 3 plus 8x minus 4 and 3 minus 5x plus x raised to the power 3. And at this moment, we cannot take the limit inside because we have the limit inside the root. This approaches infinity, the bottom approaches infinity as x approaching infinity. But we can do some algebraic manipulation to change it, excuse me. So we're going to do some algebraic manipulation next. Okay, so we can single this out and manipulate it algebraically. Okay. The same technique. We're going to divide the top and bottom by x raised to the power 3. Basically, that is the highest power, right? So this is divided by x raised to the power 3. And that is divided by x raised to the power 3. And this technique has become pretty common these days now. And so I'm trying to do it quickly. But when you do it, please do take your time, okay? Make sure you have the proper expression. And this is divided by x raised to the power 3. In fact, this step sometimes can be skipped, okay? You can go straight to the next step. You can go straight to the next step, which is, this is reduced to be 9. And this reduced to be 8 over x squared. And this stay the same. And 3 over x to the power 3, 5x over x raised to the power 3, that's 5 over x squared. And x raised to the power 3 divided by x raised to the power 3, that's 1. Okay, so you could skip this one and go straight here, but just make sure you do it right. Okay, and each one of these has a limit, right? So you can quote that theorem. Okay, actually, I want to put this in on the flashcards. Okay, so let me put this on the flashcard. Okay, so we can quote it, make it convenient for us, right? So I'm gonna put this on the flashcard. Put it here. That would be fitting. Here we go. Right, so this will be a rather useful theorem. Okay, when we deal with a composite function, which we do deal with them often. Okay, so we got that theorem, we got all these other, laws of limits, right? And yeah, we got to use this. So now, limit of each individual one exists. So we can use the limit law, the law of limits, adding, subtracting, multiplying, dividing. And we can also take this limit across the root because root function is continuous. Okay, root function is continuous. So we need to understand according to the definition as x approaching infinity, and we can work all of these out in the interval, in some interval which is mentioned in the definition, and that interval would be from a to infinity, and a being very large. Okay, a is positive and it's large. Okay, so we work all of these out in that interval. So a is positive, so all of these will work, right? Because the fact that we're using this limit notation and the definition on limit always just comes with it. And then we take limit, right? We take limit of the given expression, which is right here. The first layer, and we're adjusting our steps, right? The first one would be we will send the limit across the root, right? So we're going to have the square root and bring the limit inside. Bring that limit inside. Why can we do that? Because of this theorem. Because of this theorem. Okay, so we send it the limit across the function f. F is a continuous. Okay, f is a continuous. And by this time, you probably have assessed that the limit inside is going to be a positive number, or is going to be greater than or equal to 0. Remember, the domain for root function is just be aware of these things. Okay. The domain of root function, right, is x is greater than or equal to 0. So the limit we're coming up with must be greater than or equal to 0. Okay, so now we can apply limit law. We can apply limit law. And what are the limit laws right here, right? You can do division. We apply division, adding, subtracting, and all of that, right? So on this piece, we're basically applying this limit. So of course, we're going to replace, let's see how we replace it. Wait, we're going to first, I think we need to insert one more step, okay? So this one goes here. I'm going to bring this piece in. Okay, this piece is going to be here. and that piece, then we can put the limit inside. We do need that, we need to have that order properly because the inside limit has to exist. Then we can send it across. Now the inside limit does exist. And then we send the limit across the continuous function. And now we can take this limit to each one of them. To each one of them. There. There. Right? And then we apply limit law. We apply limit law, removing that part. And what do we have here? As x approaching infinity, right? As x approaching infinity, the limit of 9 is 9. And this piece is 0, which we're quoting this piece, right? We're quoting this theorem. So this is 0, and this is 0, and that is 0, and that is 1. So we got square root of 9. Square root of 9 is 3. Right? If we look back, when we want to find this limit basically is a square root of infinity over infinity, right? Infinity over infinity, what is the limit? Infinity over infinity, the limit may be 3. Maybe 3. So infinity over infinity, so never write it that way. Never write it that way, okay? Infinity over infinity, we don't know. We don't know, okay? So let's look at another example. Let's look at another example. This one I'm looking at is from the homework. Okay, so from the homework. I would say this one, take this one. Okay, take this one, we have limits. We want to find limits as t approaching infinity. And we have a division case, root of t plus t squared. Okay. And the denominator is 2t minus t squared. Okay. All right. As t approaching infinity, the top is approaching positive infinity, the bottom is approaching negative infinity, and we cannot take limits separately because the limit law does not apply. When we apply limit law, we must make sure the individual limit exists, right? Infinity doesn't count as limit exists. So we have to do some algebraic manipulation. So in this case, you can do it directly. You can do it directly, or you can do it separately. So you have limit, divide every term by t squared. Just be aware, right? Definition of limit as t approaching infinity, that means in some interval, right? From a to infinity, excuse me. From a to infinity, right? A is a positive, and it is large. Okay, so that is the situation. We're working with that expression. So when we divide every term by t squared, right? So we divide the top by t squared, right? We divide the bottom by t squared as well. So by this time, as you're getting better at doing this, you can just write this one, okay? And this one divided by t squared, you can just write 2 over t. Okay, And t squared by divided by t squared, that's a negative 1. Okay, now there's one more step to work this out. Root t over t squared. T is positive because t is in here. T is in this interval, so t is positive. T is positive, so root t divided by t to the power 2, that's basically, this is t to the power half. Right? Let me make the fonts larger. Okay, t to the power half, so 2 minus half, this is going to be 3 half. And wait, 3 half. 3 half. So the top is 1. Okay, so 1 over t to the power of 3 half. I mean, this writing, I hope you guys are okay with it. And right here, 2t over t squared, that's just 2 over t. Right? And then we can apply this property, right? This theorem. So that limit exists at t approaching infinity, that limit approaching 0, that limit approaching 0. You can see these are very, very commonly used. That's why it is made into a theorem, right? So as t approaching infinity, right? 1 over t to the power of 3 half, that's 0, right? When t is approaching infinity, this is 2 over t, right? Limit of 2 over t. And that's 0 as well. So we're quoting this theorem. We're quoting this theorem. So as a result, right, we can, because the individual limit exists, so we can take limit separately. So this piece, right? So this piece, we can bring it down. Now, as you're getting better and more familiar with these, right? So you can bring this limit here. You don't have to do the limit for this one because it's going to be constant anyway. So this is going to be limit. So you only have to, so these will not change its value, just so that it can stay out. Okay. And now, wait, equal. And we have 0 plus 1. 0 plus 1. And denominator is 0 minus 1. So the answer is -1. Right. So for this one, as you're getting better, your work, you don't have to show as much. Okay, some of those parts can be, simplified. Okay, let's look at another one. This other one I wish to go over is actually more of algebraic technique. Okay, so more on the algebraic technique. So when we take limit as x approaching infinity, positive infinity, we have this squared of 2x squared plus 1 and then squared. And denominator is x minus 1 squared. And then we have x squared plus x, right? Do we need to FOIL everything? If you do, you can certainly do that. If you FOIL everything, you will get polynomials on top and polynomials on the bottom with the power 4. And I leave that for you if you want to do that. But I would do it differently because I want to maintain that factor form. Okay, because we have limit law, which is multiplication. We have multiplication limit law, right? And once again, understanding this is done in an interval, which is from a to infinity by definition. right? So A is positive and A is large. So that was dictated by definition, right? The fact that we use this notation is telling us that this is the situation. So what I would do is that I'm going to divide the top. I'm going to separate the top, right? 2x squared plus 1 squared. I'm going to make it into 2x squared plus 1 times 2x squared plus 1, right? Nothing changed. Nothing changed. I just changed the way to write it. And this piece, I'm going to FOIL. Okay, I'm going to FOIL this piece. So now I'm going to FOIL this piece. That piece will turn into x squared minus 2x plus 1. FOIL. So what I would do is that for this part, I'm going to divide it by x squared. So this is what I'm going to do. Okay, to keep it simple. So I keep this piece and that piece divided by x squared separately. So I have divided by x squared, divide by x squared, and this piece divided by x squared. So top divided by x to the power 4, the bottom is also divided by x to the power 4. So principle number 1 applies, right? So I did not violate anything. And now, okay, this x squared divided into each of these. So I will get in this piece, right? I will get 2 plus 1 over x squared. 1 over x squared. Okay. And this piece, I'll do the same thing. Okay. So x squared divided into 2x squared. So these are just because these two are identical, right? So I'll keep them the same thing. The bottom, same thing, similar. Okay. So I will have 1 minus 2 over x, right? Plus 1 over x squared. 1 over x squared. And on this piece, right? On this piece, it's also similar. Wait. It's also similar. So I will get 1 plus 1 over x. Can we do this? Of course. But this will save you a lot of, possible chances to make a mistake when you FOIL the whole thing. You don't need to FOIL the whole thing. Okay, you can keep it and work with the factor form. Okay. And now we have this limit exists as x approaching infinity. Every piece, the limit exists, right? Every piece, the limit exists. Every piece, the limit exists, right? So we can quote this theorem here, right? Quote this theorem here. And then we can take the limit separately by the law of limit, the limit law, right? We can take the limit on the top, on the next step. I basically use these addition, subtraction, division of limit law all at once. Okay, so I'm going to bring this down. And I will take limits individually only on the part, right? For the constant, I just keep them the same because the limit of constant is the same, right? So this piece, so now you can do this after you become, so familiar with the law of limits. Okay, and then all of these limits, of course, is 0. And in the end, right? So this is 0. And of course, that's 0. And that's 0. And that's 0. And that's 0. And then what do we get? Right? Then what do we get? We get 2 times 2. So top is 4. The bottom is 1 times 1. So the answer is 4. We started with the expression that the top approaches infinity, the bottom approaches infinity as x approaches infinity. So infinity over infinity, the limit is what? It's 4, right? That's why never, okay? Never, ever, never, 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 ever do this, okay? You work something out, right? And you reach something, you say, oh, this is infinity over infinity. And therefore it equals to something. Never do this. Never write anything like that. Okay? Because once you're telling the reader infinity over infinity is equals to something, you know, whatever you think. No, don't do it. You're guaranteed to get 0. All right. So let us choose another number. This time it has something to do with sign. Something to do with sign. Okay. I thought it would be nice if we practice. But I do recommend before you look at what I did here, what I'm doing here, you do it yourself and then come back to compare with my work. It could be that I made a mistake. It could also be that you may need help at certain steps. Okay, so let's look at this question. So feel free to pause and you know, to do your own by yourself. But ultimately, you have to be able to do it yourself. Okay, so this is a root plus 1 plus 4x raised to the power 6. And now we have a 2 minus x raised to the power 3. But interestingly here, x is approaching negative infinity. So the definition setting is going to be from negative infinity. So we can think of x is in from negative infinity to a. And we can think of a as negative, negatively large. Negatively large, negative 10,000, negative 20,000, whatever. Okay, you can think of a number, but we just need a number, right? Right, so this is the setting. We are working with this expression, right? And we're going to work algebraically. We're going to work out algebraically. So here, I'm going to just work on this straight. Okay, you can do the separate things. Okay. So I would divide the top and bottom by x raised to the power 3. Which seems to be the most natural thing to do. Divide by x raised to the power 3, so this is a 1. So this piece is going to be divided by x raised to the power 3. Now question comes. Okay, we want to bring this x raised to the power 3 inside the root. And what do we have here? Okay, you may like to pause here to work out your solution, because from x raised to the power 3, so what do we have here is x raised to the power 3, okay, and then squares. Okay, so let's do this. Let's do this. Okay, squared, right? It equals to what? What does it equal to? Absolute value of omega. Okay, this Greek letter is read as omega. And now we have that famous function, right? Everybody's familiar with it. If omega is greater than equals to 0, the absolute value of omega is the same as omega. If omega is negative, the absolute value of omega is its opposite. Right? We just use omega is just a placeholder. I think I can make the fonts a little bit smaller. Okay. So now, suppose omega now omega is in the negative category, right? So we're considering this category. And our omega is x raised to the power 3. Okay, so that's our omega. Okay, x raised to the power 3. So this is x raised to the power 3. This is x raised to the power 3. This is x raised to the power 3. X raised to the power 3. This is x raised to the power 3, by the way. Right? Because x is in this interval. So x to the power 3 is also negative. So basically we have, what do we have here? So let me put this under. What do we have here? Right? Basically this says x raised to the power 6 in the square root. Right? X raised to the power 6 in the square root is equal to negative x raised to the power 3 when x is negative. Okay? And here x is negative. So that's the relationship. So when we substitute x raised to the power 3 and we want to bring this to the square root, and that's what we're getting. So the next step, okay, x to the power 3 will be replaced, right? You multiply negative, put a negative sign on this other side. So x raised to the power 3, you bring this negative sign to the other side. So that's going to be this piece replacing x raised to the power 3. Okay. I see this is the part that needs some, tender loving care. Okay. Once you have this, great. Once we have this, we can, so on the one hand, we have an extra negative sign. So I'm going to put it in the front. Okay. Just for safekeeping. Okay, I'm going to carry it everywhere. And these two square root, I'm going to put them under the same square root, right? So I'm going to do this, right? Put them under the same roof, right? And nothing need to be changed in the bottom. And so now we have this negative sign safely there, and then x to the power 6 divided into 1, and then 4x to the power 6 divided by x to the power 6, that's going to be 1, right? Oh, 4, sorry, it's going to be 4. Every limit exists. Therefore, we can take the limit inside. And the square root is a continuous function, so we can take the limit across the function, across the continuous function, right? So what do we got now? Our next step, right? Our next step should be, I'll take this limit. Wait, yeah, I put a negative sign in the wrong place. Okay, hold on. Put the negative sign here. Okay, put a negative sign here. It's just a typesetting issue. Okay, it's just a typesetting issue. And there's a negative sign here, don't forget, right? So now I'm going to take this limit across the continuous function, and limit of 4 is going to be 4. So I'm not going to do that. So now, according to this theorem, right? And that piece is 0, that piece is 0. What do we get? Let's see what we get. Right? So this is 0. That is 0. So root 4 is 2 over negative 1, and there's another negative sign. So the final answer is a positive 2. Okay. Let's see, I think we we can work out 27, 28. Okay, these are in your homework, right? These are in your homework. One is taking limit to positive infinity. One is taking limit to negative infinity. So you get to practice that all over again. All over again. I would just do one. Okay, I'll do one of it and save some for you. Save some for you. Okay. I don't want to make this too long because there's some other types of questions that we need to consider here. Let's do the 28th, right? Do the 28th. And this question, I don't know which example this is this now. Let's count. Let's count. Okay. Example number 1. Can this say example number 1? Right? That is T. And that's example number 2. Number 2. Example number 3. Is it? No. This is 2. Oh, that is 3. 3, 4. Example number 4. We're done 4. That's good. Number 5. This is number 5. And this one, we also get to, because of negative infinity, right? So we have limit as x approaching negative infinity, but I do highly recommend you try your own before you watch mine. Okay, and we have a square root of 4x squared plus 3x plus 2x outside the root. Okay, I make sure I copy the question correctly. And what kind of situation do we have? All right. When x is approaching negative infinity, this piece after x squared, this is approaching positive infinity. 4x approaching negative infinity. So we have an infinity minus infinity, right? Does the infinity minus infinity equal 0? We don't know. We don't know. Okay? And we cannot take the limit individually. We cannot and never ever do this. Can't do this. Cannot do the following. Okay? You would take limit like that, right? Bring the limit in here. If you ever do this, it's guaranteed you're gonna get a 0. So please, please don't do that. Why? The former is positive infinity, the latter is negative infinity. Can you say infinity minus infinity is 0? Well, I certainly don't. I've seen that kind of work before. Why we cannot do this? Why we cannot do this? Okay, why we cannot do this? Because the law of limits does not apply. The law of limit requires the individual limit must exist. This individual limit does not exist. This individual limit does not exist, even though they do approach infinity and negative infinity, but infinity are not limits. Okay, so don't you ever do this. Don't you ever do this, okay? So I'm going to put this under, right, as a note. So don't you ever do that, please. Okay, so what can we do? You probably guessed it. This is a similar type that you're going to need to do rationalization. Okay, rationalizing the numerator by multiplying by 1 And you're going to multiply the conjugate. And the conjugate of this piece is, of course, is minus 2x, right? And minus 2x. This is the one. In what kind of setting? X is approaching infinity, right? So we're in the setting of what? X is in the interval from negative infinity to an A, and A is negative. It's a negative large number. It's a negatively large number. Okay, so that's the setting we're working with these expressions. Okay, and next, conjugate, right? Conjugate. So we keep that. And we have a denominator now. The denominator is this piece, right? We have that denominator. On the numerator, we have A plus B times A minus B, right? So if you like to work on your scratch paper, so this piece, right? Multiply that piece. That's going to be A squared minus B squared. So that's equals to this piece squared minus 2x squared. Whoops, 2x squared. Okay, so that's what we're getting. Okay, so right here. And then what do we get? We have to organize the term a little bit. Okay, and this piece, right, root, we're going to apply that root of something squared equals to x. Okay, don't get confused. Root of x squared, that is equals to absolute value of x. We talked about this before. Okay, just be aware. If you still have questions, please don't hesitate to ask me. Okay, now this piece is that, right? Apply to that. So 4x squared plus 3x. That's what we got from here. And 2x squared is that's 4x squared. Right? And next, 4x squared and 4x squared, they're reduced. So we only have 3x left. Then what do? We still cannot stick limit inside. Why? Because as x approaching negative infinity, the bottom approaching, oh, this is 2x. I'm sorry, did I? Oh yeah, this is 2x. How did I do that? 2x. Yeah, I'm glad I found it. Otherwise, nobody's here to tell me, right? I'll be stuck. So you see, in this situation, we still cannot do anything. Why? Because as x approaching negative infinity, the top approaching negative infinity, the bottom approaching positive infinity minus negative infinity, right? And we still cannot use the limit law. What do? That's right, we're going to divide the top and bottom by x. We're going to divide the top and bottom by x. So this divided by x, well, x is negatively large, right? We can do that. This piece divided by x, and that piece divided by x, right? And then what do we get? 3x divided by x, that's a 3. 2x divided by x, that's a 2. And what are we going to do about this piece? That's right. We want to bring the x inside the root. But we already have some ready to use principles we have done before, right? So that is right? When x is negative, right? When x is negative, x squared, which is equal to absolute value of x, right? X is negative, it is opposite. Okay, so now what does that tell us? If we remove this piece, this is just a bridge, we know x root x squared is negative x. As a result, right, we get x equals to negative square root of x. Here, I'm using arrow. Arrow means that from here, we get this, okay? I could have written the next line, but to not make it too messy, that's how I write it, right? So now, on the next step, I don't do anything. I just replace this x by its equal. Boom. Boom. Oh, 2. That's good. Okay. And then what? I have an extra negative sign here, so I'm going to bring this negative sign to the front. And I'm going to bring the whole of this in 1 square root, right? So I'm going to bring this in 1 square root. So this piece divided by x squared. And next, you can see x squared divided into 4x squared, that's going to be 4, right? And 3x divided by x squared, that's going to be 3 over x. Finally, things are looking good. Okay, please check your work. Okay, so you don't make mistake like I did. Okay, luckily I found it. Now each term has a limit. Okay, limit can be taken across the continuous function, which is a root function. Now we can apply limit law. Before all of these, we cannot. Only now in the next step, we can apply the law of limit. You can certainly do the algebraic part separately, but I'm not doing that. I just want to have a, have a nice flow. So I'm going to take this limit only to that part because the rest of them, they are just constant, right? And next step, this whole thing, right? The limit here is 0. Oops, 0. Root 4 is, here, sorry. Here, 0 is equal, right? That's equal. So what do we have? We have root 4 is 2. So negative 2 minus 2, that's going to be negative 3/4. 3/4. So now if we look back, right, we have a situation like this. We ended up with a limit of negative 3/4. Remember, we talk about this as x approaching negative infinity. This is a positive infinity. This is the infinity, negative infinity. So positive infinity minus negative infinity, is it equals to 0? No, you can't do that, right? Remember, I told you what they cannot do, right? So you really, really cannot do that. In this case, the limit is a negative 3/4. Okay, the limit is negative 3/4. And these algebraic manipulation can be done separately, Okay. There are a couple of the limit like doesn't exist. So for example, right? For example, this one. This is example number 5. So let's look at example number 6. Right? We have a limit. Okay, this limit, right? X is approaching infinity, positive infinity, and we have a function e to the power x plus 2 times cosine 3x. And we're looking at this limit. You may like to take a second to try this by yourself. In this example, let me make sure I copy the question correctly. This is a negative x here. What will be the limit? And we take limits separately. Okay. You know, when we look at the individual limits, there's a limit x to infinity, right? We know this function. When we take a limit, let's just think out about. Allowed. Okay, I'm working this out on the scratch paper. So limit on e to the power negative x, right? We have discussed this function as x approaching infinity, e to the power negative x is going to be like this, right? If you don't remember the graph, or, you know, that's okay. You just know that as x approaching infinity, e to the power x is approaching infinity. So this whole thing, right, that's 0. That's limit is 0. As x approaching infinity, denominator is infinitely large. But how about the individual limit here? The individual limit for 2 times cosine 3x. This limit does not exist because as x approaching infinity, cosine, this is a cosine function. If you times 2, it's oscillating between -2 and +2. You can look at the graph. Right, you can look at the graph. It's just oscillating between -2 and +2. Okay. So this limit does not exist. This limit does not exist, right? So this limit does not exist. Does not exist. As a result, the limit law does not apply. So you cannot take limits separately. Okay? The only thing you can think of is that this quantity is approaching 0, but this number is always uncertain. So this whole thing, when we take a limit of the sum of a number approaching 0 plus a number that's never certain, is always oscillating, and that would be does not exist. Okay, so that's how you would think about it. There are other similar examples. Okay, there are other similar examples, but you know, it's just yeah, there are a couple other examples in your homework, and I trust you guys can figure this out. Otherwise, ask me. Okay, so example number 7. Okay, example number 7, I'm taking this limit. Okay, x is approaching positive infinity, and we got an arctan of e to the power x. Okay, the parentheses actually is optional here. Arctangent is a function that is continuous function on entire domain, which is a number line. So as x approaching infinity, e to the power x approaching infinity, but we cannot bring the limit inside though, because infinity is not considered a finite number. We just know e to the power x is approaching positive infinity, right? So you can say as x approaching infinity, e to the power x is approaching positive infinity. And as you know, arctangent approaching positive infinities, the property we can use here is this piece, arctan as x approaching positive infinity, so e to the power x approaching positive infinity. So the limit is going to be pi over 2. Oops, pi over 2. So that should be an easy one. I do want to take the next one, because for the next one, you get to use a different method to find the limit. Example number 8. This limit we're looking for is as x approaching infinity, right? We have a ratio of sine squared of x over x squared plus 1. Can we take limit individually? The answer is no, of course. But can we use the techniques that we're dividing by x squared? Well, you could, but it would be so much better. Actually, we can use the squeeze theorem here. Okay? Because sine x squared, right? That's always greater than or equal to 0 as x approaching infinity. Remember, we work this expression under the limit, and which means the limit definition applies. So it's from a to positive infinity, right? Where a is positive and large. But even for a is large, sine square of x is oscillating between -1 and +1, but if you square it, it's going to be oscillating between 0 and 1. Okay, I can show you this. You don't have to see the picture. You just need to know that sine x is sine x squared, right? We know sine, right? Sine x is between -1 to +1. Between +1 and -1. Right? That's for any x. Okay? That's for any x. Let me find that symbol. Okay, you guys. I think some of you guys like to use those symbols. For any. Where is it? For any. Wait. For any. Where's that symbol? The upside down A. Here, there. For any x. For any real number x. But when we square it, right? Sine x squared is between 0 and 1. So this is going to be between 0 and 1. Right? And if we multiply 1 over x squared, we're divided by 1 over x squared, right? So we divide this by x squared plus 1. We divide this by x squared plus 1. Divide this piece by x squared plus 1. So our given function is squeezed in between. Is a squeeze in between. And that is 0, of course, right? And then we take limit. So this is the limit below, this is limit above, and this is already 0. So the limit of this piece, right? The limit of that function, according to theorem, that limit is 0. And this piece is squeezed in between, of course, that limit is going to be 0. Okay, so you can say by squeeze theorem, that limit equals to 0. Okay. All right. And the other functions, okay, I think I don't know how long it has been. Okay, so let me just push forward anyway, right? Because I don't want to make too many. Example number 9. I would like you to look at the limit of this function, e to the power of negative 2x multiply cosine x. Okay, and there's a parentheses. So we're taking a limit on this piece. What kind of situation is this? Well, we cannot separately find the limit because the limit for x to the power 2e to the power negative 2x, that limit exists, but cosine x does not have limit. It's oscillate between negative 1 and 1. So we cannot apply limit law of product. We cannot. What do we do? We could actually use squeeze theorem again, okay? Because we know e to the power negative 2x is always positive, right? But one fact we like to point out is e to the power of anything. Anything is always positive, okay, no matter what, okay? And the other fact is that cosine is between negative 1 and positive 1 for any x, for any x, right? So for any x, we've done it before, so I'm going to copy this piece and just put it here. For any x, if e to the power of anything is, right, is positive, negative 2x, e to the power negative 2x is positive. That's the range of e to the e function, right? So based on these two facts, I'm going to multiply e to the power 2x on every side, okay? On this side, and on this side. But it is still true. And that is still true for any x. But the setting we're considering the x is what kind of setting? Yes, it's the setting given in the definition, right? A is positive and A is large. A is positive and large. And of course, it's also true. So our x belongs to this interval. So x is positive. So if it's true for any x, certainly it's true for positive x, right? So that's the interval that's the setting we're considering this. So now the given function is squeezed in between, right? In between. So this is a negative, and that can be removed. And the limit of e to the power negative 2x is 0 as x approaching positive infinity. So this is 0, right? So this limit is 0. And therefore, by squeeze theorem, that whole limit is 0. You can see squeeze theorem actually is pretty useful, right? It's pretty useful. Okay. Let's do another one. Example number 10. Okay. We have a limit. We have a limit here. Limit as x approaching 0, right? We were talking about limit at infinity. Why all of a sudden we have a, approaching 0 from larger than 0? That's interesting. So we get an arctangent and we have ln x. Ln x should be a function we're pretty familiar with, okay? But I'm going to bring it up anyway. Ln x, if you think out aloud, right? Ln x has a domain. Domain is x must be greater than 0. X must be greater than 0. That explains why we let x approaching 0 from larger than 0. So for those of you who are familiar with this, or not, if you're not familiar, please get familiar with this function. You can find some, recording on this function in the first week, right? And I'm going to make some adjustment on the view. And this will be 2. How that look, right? So when x is approaching negative, when x is approaching 0, when x is approaching 0, right? The logarithm function ln approaches negative infinity. Okay, ln approaches negative infinity. It could go as low as possible. And the range, of course, right? The range of this function, of course, right? The range of that function is from negative infinity. This is a very important function. And you're going to use this function in your calculus, the following classes. I'm going to use this function throughout this course. Okay? So the range, right? Familiar? Okay? So when x is approaching 0 from larger than 0, ln x approaching negative infinity. Okay, ln x approaches negative infinity. Well, ln x approaching negative infinity, which property would apply here? This piece. Okay, this piece would apply here. Wait, why doesn't it show me this one? Why it doesn't get that star over here? No. Wait a second. I hope these are recorded. Is it recorded? Okay, it's recorded. All right. For a moment, I thought it's not recorded. Pause the recording. Okay, it is recording. Okay. All right. Okay, so we're using this because ln x approaching negative infinity for the entire limit now is going to be approaching negative pi over 2. Right, you can see these actually just rely on some basic knowledge, right? Rely on some basic knowledge like this on the functions we have learned before, right? So this piece, right? So why doesn't it let me draw here? I don't know why, but anyway, it's okay. Last but not least, I think I'll just do one more. It's time to close this. Okay, example number 11. Okay, I choose a question which is involving logarithm. Okay, so we have a limit. Okay, this limit is x approaching positive infinity. X approaching positive infinity, and we have natural logarithm of 1 plus x squared minus ln of 1 plus x. Okay, x approaching constant infinity. So the setting of considering this limit, of course, is still the same as here, right? By definition. So that's the setting we're considering the limit. Okay, I try to, try to save time. Okay, but the thing is, how do we handle logarithm? Well, in logarithm, we know there's a quotient rule. Okay, so when we handle the algebraic part, we have ln, right? The quotient rule allow us to do 1 plus x squared divided by 1 plus x. Right, so when we are taking this limit, we're taking this limit. Can we reduce this function? The answer is no. The answer is no. When we take limit inside, well, ln is a continuous function, but inside the function inside does not have limit. Does not have limit. Okay. Why? How do I know that? Okay, so if we think out loud, let's suppose we do this on the scratch paper. Think out aloud. Okay, we think out aloud. Only algebraically we can do this, and we cannot reduce it. Unfortunately, we can't. And if you're thinking taking the limit inside, right? If you're taking the limit inside, you're quoting this theorem, right? This theorem requires that f is continuous, but it's also required the limit inside has to exist, right? And so we're checking to see if the limit on this piece, does that exist as x approaching infinity? It doesn't. It doesn't, because you can divide by x squared, right? You can divide by x squared, but what do we end up with? So you divide this by x squared. You divide by x squared, right? So this will be x under 1. You divide by x squared, so this is going to be 1 over x squared. And you divide by x squared, that's going to be 1. So as x approaching positive infinity, the bottom is approaching 0. The top is approaching 1. So this limit does not exist. It's actually approaching positive infinity. You cannot bring the limit inside. So you can, when you assess the inside, right? This limit, you're taking limit of infinity when ln x, when x approaching infinity, ln x also approaches infinity. So the final answer for this one is that the limit doesn't exist and the limit is positive infinity. Okay, so sometimes the limit does not exist. So you need these knowledge to handle. You also need to know, the limit. We learned this in earlier sections at 2.3 or something like that. Okay. The next one, however, okay, let's do one more. Example number 12. The next one, however, maybe. Okay. And this one is also about logarithm. And the setting is also x approaching positive infinity. The only thing that is different is that the function is slightly different. So this is a 2 plus x and the minus ln 1 plus x approaching positive infinity. So it's still the same environment, limited environment. But in this case, right, if you look at the algebra part, we're gonna handle the algebra part, and that's gonna be ln, right? 2 plus x divided by 1 plus x. And if you look at the limits, right? If you look at the limit, as x approaching infinity, I'm taking the condition here. As x approaching infinity. This piece equals to, we cannot take the limit directly, but we can divide the top and bottom by x. Okay, so this divided by x, and this divided by x is 1, and this divided by x, and this divided by x as 1. Why this limit exists, so we can take the individual limit, right? We can take the individual limit, and that limit, we can take the individual limit, right? And that equals to 1. Now we can apply this theorem, because the limit of the inside function exists, so we can, and the function ln x is continuous, so we can bring the limit across, and now we can carry it out of work. Okay, so you can still keep the step to show your work. You just show it step by step, right? So at this point, okay, and you can say the next step, you're going to write limit, right? Limit, but you're going to replace this piece by that, right? So this piece replaced, right? And bring the limit across the continuous function. So you have ln, you bring the limit inside over here, put a parentheses, right? Just like we have the function here, just like this property, okay, this theorem. And that limit already found, right? If you want to skip the algebra part, or you just copy the result, you can do that, right? Or you can just repeat this piece, okay, replacing this part, right? One more. This way you don't have to show this piece, okay? And now we got that, right? And then almost done. And this piece, we got ln 1, right? So we have 1. So this whole limit is 1. ln 1, we can remove the parentheses, is equal to 0. Okay, so in the end, when you look at this question, right, you think about it, and this equals to 0, right? As x approaching positive infinity, this piece approaching positive infinity, this approaching positive infinity, in positive infinity minus infinity, hey, we got 0. So we have seen such a situation, right? Infinity minus infinity, is it equal to 0? Sometimes it does, sometimes it doesn't, right? So in some situation, it's not, right? Like in this situation, the limit is not 0, right? The limit is -3/4, even though you have an infinity minus infinity case. So never ever write infinity minus infinity equals 0, okay? It sets you up for getting a 0, getting a 0. So every question you do, make sure you really think through it by applying these properties and theorems, because that's really how and what we assess your study on, okay? But anyway, thank you for watching. Until next time, bye.